Good day, I'm Maile Matsiba. Welcome back to our channel. We're continuing today with our 2017 study guide of our CIR 113 module. We're looking at example 2.11.1. Now, it says an irregular shaped object has a mass of 4 kilograms and it is necessary to find its volume and density. It continues to say the object is immersed in water with an Hg of 1, and then found to have a weight of 2.3 kilograms. Now, for us to be able to answer this question, the first step we need to take is actually to calculate the weight loss of the object. Remember, they are telling us that it actually weighs 4 kilograms, and after it was immersed in water, it then weighs 2.3 kilograms. So we're going to be using the principle that we study now, the Bayon's principle, and we're going to be calculating the weight loss of the object. So we can just say step 1, calculate the weight loss we can put it in brackets because in reality it doesn't really lose weight, but because of the effects of the water, it appears or it behaves as if it has lost weight. So we can just put it, that is what the quotation marks are. So calculate the weight loss of the object Now, for us to do that, we can just say apparent weight loss equals to the weight of object, excuse my handwriting, the weight of this object, the weight of the object minus the weight of body, or rather object, in water. So that is our equation, and we can continue further just to make the equation much more clearer and say we can say it's the mass of the object multiplied by a gravitational constant. Here is actually this weight, the original weight, then minus the mass of object in water, also multiplied by the gravitational constant. Now we have then 4 kilograms. This is because the original mass is actually 4 kilograms, multiplied by our g, or gravitational constant, is 9.8 meters per second squared, minus the weight of the object in water is 2.3 kilograms, multiplied by also g is 9.8 meters per second squared. So that is our g, and if you do the calculation, you arrive at 16.66 kilograms meters per second squared. So now that is the weight, but to make it much more clearer, we can actually say it's 16.66 newtons. This is because, can I just write in brackets, a newton equals to kilograms meters per second squared. So this is actually a newton, so hence we could easily replace this with a newton here. So the weight loss of the apparent weight loss of the object as a result of the effects of the water is actually 16.66 newtons. Now, another important thing that we know is that the weight loss of the object in water, when it's in water, it's equal to the weight of the water that is displaced. This is just something that we know. It's a principle that we learned. So I just want to write it here so that as we move forward, we keep it in mind. Let me just say we know that the weight loss of the object is equals, let me just say equals to the weight of the water that is displaced. This is something that we don't need to figure out or calculate. It's a principle that we know we learned throughout the chapter. So now, with that said, now that we know that the weight loss, which is this one, is actually equals to the weight of the water displaced, then we can move on to our step 2 and say step 2, we can calculate the mass of the water that is displaced. And for us to do that, we can use the normal equation that we know, weight equals to mass by g. So it's equals to weight, let me just highlight here that it's the weight of the water displaced, equals to the mass of the water displaced multiplied by g, or our gravitational constant. Now if you do rearrangements, we can just say the mass of the water displaced equals to the weight can I just write it properly? Sorry about that. Let me write it in such a way that it will easily be visible. The weight of the water displaced all over g. I just rearranged this equation so that I can have the mass as the subject of the formula. So now with that said, we can actually plug in our equation. Remember, we know that the weight of the water displaced is equals to the weight loss of the object, and we know the weight loss of the object is actually 16.66 newtons. With that said, then we can actually decide to actually say 16.66. we can either use kilograms, meters per second squared, or newtons. Allow me to use this one because I'm going to divide with g. It's going to be easy for you to follow up as I'm going to be cancelling a few of this here. So let me say kilograms, meters per second squared, but at least it's important to know that this is actually newtons all over. Our g, we know it's 9.8 meters per second squared. Now this gives us 1.7 kilograms. Remember, we calculating the mass, and with this said, if you do the rearrangement here, you're going to notice that this cancels this and this cancels this, and then we're left with kilogram. So, and 16.6 is divided by 9.8, it gives us 1.7 kilograms. That's why I actually opted to using the actual full newton other than just the symbol, just so that I can explain to you how we got to the kilograms. So that is actually what we just calculated. So now I want us to go to our step 3, and now that we have all the information we have, we can calculate the volume of the water displaced. Remember the question, the original question was saying calculate, it is necessary to find both the volume of the and the density of the object. So now what we're going to be doing, now that we have remember we want the volume and the density of the object. So now that we have all the information, what we're going to do now is we're going to be calculating the volume of the water that has been displaced. So let me say step 3. I hope it's clearly visible here. Step 3, calculate the volume of the water that has been displaced. Yeah, so that is actually our step 3. So with that said, if we're going to actually calculate, we know that density, this is a general equation, density equals to mass all over volume. Now, with that said, we can actually say that the volume of the water displaced, the volume of the water displaced equals to the mass, the mass of the water displaced all over the density of water, or of the water displaced. It's actually the same, they're all water. So now, with that said, we already know that from what, let me just bring it here, from what we calculated, we know the mass of the water displaced is actually 1.7 kilograms. So we can just say equals to 1.7 kilograms all over the density of the water. We have been given it to have an Sg of 1, and we know that an Sg of 1 means 1 kilograms per liter. In many of our previous equations, sessions or examples, we actually talked about that, so I don't really need to calculate it. So it's 1 kilogram per liter. Now this gives us 1.7 liters. Now we have calculated, let me just bring back the equation so we can be able to see it. They say they want the volume and the density of the mass, but now we have calculated the volume and the density of the water that has been not the density, sorry, the density we know. We've calculated the volume of the water that has been displaced. So we're going to use yet another principle that we know. We know full well that the volume of the object is going to be, let me just say, the volume of the object is equals to 1.7 liters. Now I need to explain why and give a reason. The reason is because we know from principle that if the body is fully immersed, then the volume of the water displaced equals to the volume of the body immersed. So I can just write it here, because if the body, if the object, if the object is fully immersed, if the object is fully immersed, then in principle we know that the volume of the water displaced, volume of the water displaced equals to, or equals the volume of the object immersed. This is from principle. This is something that we learn. Now we have the volume of the water, or rather of the object already, and we have answered one part of our question. Remember, they say it's necessary to find both the volume and the density. So now that we have the volume, we can just use the equation of density and say density of the object equals to the mass over volume. Then equals to the mass. We're using the original mass because we know the original mass of the object. We have been given it to be 4 kilograms. So we know it's 4 kilograms all over the volume. We calculated to be 1.7 liters all over 1.7 liters. And when you use a calculator, you get 2.35 kilograms per liters. So that's what it is. Or you can say energy, it's G equals to 2.35. So that's basically how to answer this question. And thank you for your time. I hope we meet again in our next video.